All.
Good morning, sir.
Yeah, good morning. First of all, very good morning to you all. For the last couple of the classes, we were discussing about the stability analysis of various slopes. So, by different methods. Before we begin our today's lecture, if anybody has any kind of a questions, I'll be most happy to answer. Anybody has any question? Okay. So, if you don't have any questions, so let me go ahead. A couple of points that I thought we have already missed it. So therefore, I'll be going to cover all those important miss points in this presentation. So let me try to cover up all those aspects or all those important points. One of the important thing is we have discussed in detail about the Taylor stability number and the Taylor stability analysis procedure. So this is a complete outcome of the Taylor's contribution. So he has given a predefined curve, that is predefined graph between stability number m versus the slope angle beta. Again, as a function of different parameters, as we have already discussed. For example, if a firm stratum exists at a depth of d from the top of the embankment, then how to determine the critical height of the embankment. That is one aspect. The second aspect is, so from the toe, if the predicted or if the assumed failure slip circle is a base failure, so where the other end of the slip circle emerges from the toe of the slope. So is it within our boundary or is it behind our boundary? So for such assessment, so the Taylor's analysis is most useful. Now, if you look at these predefined graph, so at beta is equals to 53. So if the value of the slope is less than 53, it could be either toe failure or midpoint or slope failure. Or if it is beta is above 53, it is definitely going to be only the slope failure. So that's what is the contribution or the conclusion by the Taylor. As for this chart, we can also understand the same thing. Now, suppose if you know at what depth the firm hard stratum exists, depending upon that one, we can able to determine the critical height of the embankment. Critical height of the embankment. So that thing can be understood from this graph. Suppose if the D is 4, 2, 1 or so on and so forth, if the beta angle is known, then draw a corresponding to beta angle, a vertical line onto any of these curves. Then from there, draw another horizontal line onto the stability number. Onto the stability number. So this is something like this. Suppose if the beta is say 25 and D is say 1.2. So from here, you draw another horizontal line onto the ordinate. So this will give you the stability number m. So you know the basic definition, stability number m is equals to gamma d by CD by gamma h. So if the CD is known, gamma is known, h critical can be determined. So this is how this predefined chart is used for practical applications. So some assumptions are given. Limitations of this figure valid for slopes of saturated clay only, applicable to only undrained conditions, that is pi is equals to 0. So the same thing, in fact. Then another important thing is, so suppose if you are using the same Taylor's analysis for determining the factor of safety, how to identify the center of the toe circle, So as we can witness, so from this right side topmost picture, so O is the center of the circle and theta is the angle between two edges of exit and end points of the toe circle. So where alpha is the chord angle and beta is the slope angle. So here also another predefined correlation has been given between the slope angle beta and other parameters like alpha and theta. So here you can see alpha is the angle, the chord angle between the toe circle. So and theta is the angle, acute angle between the exit and emergence points of the toe circle. So here, so if you know the theta, if you know the alpha, then you can able to determine the location of the center of the toe circle. Again, when I say or when we state that the failure is in the toe failure mode, so it is obvious that the beta is greater than the 53 degrees centigrade. So that is, so as we understood from the previous class. Or alternatively, you can able to determine the radius of the critical slip circle R is equals to H critical divided by 2 sin alpha into sin theta by 2. So you can also use this equation to determine the radius of the slip circle. Or if you know the other values, then you can also identify the center of the toe circle. So this is how the center of the toe circle is identified in the Taylor stability number. Then the another important contribution of the Taylor's analysis is, so from the toe, at what length the toe failure, the toe circle emerges. So for that purpose, he has proposed another predefined correlation between slope angle beta and d, that is the depth from the top of the embankment to the form stratum, and the distance, that is n. So here you can see for n is equals to 0 indicates the toe failure, n is equals to 1, 2, 3, so on and so forth. So for the known beta angle and for the known the depth of the hard stratum, we can able to predict from this predefined graph, so where possibly or likely the toe circle emerges on the ground surface. It's a quite simple to understand. So this is another way. In the last slide, we were discussing about how to identify the center of the toe circle if the beta is greater than 53 degrees centigrade. But what about the identification of the center of the toe circle if the beta or the slope is maybe toe or maybe slope failure? So in such a situation, how to identify the center of the toe circle? So this is the center of the toe circle. So here also they have given different values. Suppose if you look at this table 15.1, the location of the center of the critical toe circle for beta less than 53. This is n dash. So for that purpose, we need to know 3 or 4 values. The first is the slope angle, 1:1 or 1:2 or 1:3 or 1:4. That is represented in the form of n dash. Well, that is 1. 1 means 1:1. So 1:5, sorry, 1.5, 2, 3, 5 up to. So for different slope angles. That means your n dash is equivalent to some beta value. Suppose if it is 1:1, it is 45 degree. So 1.5 means 33 degree, 2 means 26, 3 means 18, and 5 means 11. So this is the relationship between n dash versus beta. So both are same. Now once beta is known, for a known beta, now the other values of angles, that is alpha 1 and alpha 2, either you have to assume or you have to determine. You have to determine the location of these circles. Like for example here, for a few values of the 28 of alpha 1 and 37 of alpha 2. So you can able to identify, you can able to draw. So two arcs wherever these two arcs will meet, so that will become the center of the toe circle. So in case where the beta is less than 53 degrees centigrade. Okay, so this is how the center of the slip circle or the center of the failure circle will be identified in case of beta less than 53 degrees centigrade. So this is we have already discussed. So this is a small demonstration how to use this graph, the Taylor's stability chart, for determining various parameters. So for example here, if I know the slope angle, that is beta is equal to 60 degree, height of the embankment, gamma and Cu. So how I can able to determine the minimum factor of safety value. So first of all, these are the steps that has been given. Say beta is equals to 60, beta is equals to 60. So corresponding to 60, draw a vertical line. So this vertical line meets this predefined trend lines. Say for example, at beta is equal to 60, it is meeting here. This wherever this intersection is there, from this intersection, you try to draw another horizontal line onto the ordinate. So which gives or which would yield the stability number m value. Stability number m value. So here, for example, a b for beta is equal to 60, m is 0.195. So if you draw vertical line where it intersects the trend line, and from there if you draw an horizontal line, so it is giving a stability number of 0.195. So if I know the stability number m, and from there I can able to calculate the CD. For example, CD is equals to gamma h into m, or m is equals to CD by gamma h. Now I know the m value, I know the h value, I know the gamma value, so I can able to determine the cohesion, desired cohesion value. So in a sense, if slope angle is fixed, you can back calculate what would be the minimum cohesion required to withstand such slope. So calculate the Fs, that is Cu divided by CD. So that means factor of safety in terms of the cohesion. So where Cu is undrained cohesion, CD is the cohesion determined based on the stability chart. So this is how the factor of safety is determined. On the other hand, so we have given the one demonstration for beta greater than 53. Now let us try to understand for the beta less than 53. So example, I assumed beta is equals to 30 degree and h is known, gamma is known, so Cu is known, depth to the hard stratum, so HD is known. So then what would be the minimum factor of safety value? So this is also straightforward. Now here, but unlike the previous case where it is directly intersecting with only single line, but here beta is less than 53, so there you could find that there are different trend lines corresponding to different values of the D. So first of all, you need to determine the value of the D, which is defined as distance from the top surface of the slope to the firm base by height of the slope. Height of the slope. So first calculate the D value, because you need to pick up one of these trend line, HD by H. So once this is known, and from the known beta angle corresponding to 30, draw one vertical line wherever it is meeting the calculated D line. Calculated D line. So for example, here it is 30. So draw a vertical line. So here HD by D is approximately 2. Approximately 2. So from there you draw another horizontal line. So that will give you the stability value, that is M. So here M is equals to 0.178. So once I know the M, I know the relationship, that is M is equals to CD by gamma H. So I know the M value, I can back calculate the desired cohesion. So I know the Cu value again. So the factor of safety is nothing but Cu by CD. So CD is calculated from the stability chart. Cu is experimentally obtained in the either in the field or in the laboratory. So the ratio between Cu by CD will give you the least or the minimum possible factor of safety. However, this may not be minimum. Remember, this may not be a minimum value, but this is some factor of safety value. So that's what about the Taylor's stability chart. So this all these problems we will discuss maybe when we discuss about the tutorial. So let me show the other parts. Yeah. Now we also did discuss about the friction circle method, that is slopes in homogeneous C-pi soil. So there also we arrived at a conclusion that C dash by gamma h is a function of alpha comma beta comma theta comma pi dash, which is again correlated with the stability number m. So based on this derivation also we have tried to understood the friction circle method, r sin phi, so on and so forth. But ultimately we arrived at the equation, that is C dash by gamma h critical is equals to m, that is the stability chart. So here also in order to verify or validate the theory of the stability chart to the C5 soil, because the previous discussion was varied only for pi is equals to 0 soil. But here we are dealing with the C5 soil. So therefore here you can see another predefined chart. The stability number M, which is correlated with the slope angle beta and the soil friction angle pi. So the pi is in the x-axis, stability number is y-axis, and there are various different trend lines corresponding to different slope angles, starting from 90 and ending at 10. So 90 means almost vertical slope, 10 means the very steep, very gentle slope, Okay, so here suppose if I know the slope angle and if I know the friction angle, I can able to pick up the value of the M. So one question may arise in everybody's mind. So here the trend lines have been given for a interval of 5 or 10. So what if suppose say for example the beta is 10 here and the beta is 15 here. So what if my beta angle is 12? Then in that case you need to interpolate. So this is a common philosophy, so that I don't need to reiterate again. So if any line is lying between the given two angles, you need to do interpolation with that. And this is a procedure. So there are steps which has been given to determine the factor of safety. So in case of the C5 soils, that is friction circle method. So first step 1, determine C dash, pi dash, gamma, beta and H, either from the field or from the laboratory experiments. So first determine C dash, pi dash, gamma, beta and H. Now in a next step, you need to assume the one or initial value of the pi dash d. Okay, so you can understand in such a way that if pi dash is the angle of internal friction at failure, where pi dash d is the angle of internal friction which is required to mobilize the failure, just to mobilize the failure, or it may be lower than that. So you need to keep on assume that values. Okay, so suppose if the pi dash has been given as 25, so you can assume pi dash d may be starting from the 15. So initially assume pi dash d as 15 and do follow the procedure to calculate the factor of safety. So for example, initially I assumed some value of the pi dash d, say 15 degrees centigrade. So then say in step 1 in the column 1, I assumed the pi dash d value. Then in step 2, so try to calculate the factor of safety, F pi, that is factor of safety as a function of the friction, which is defined as tan pi dash divided by tan pi dash d. So tan pi dash is a given value, tan pi dash d is assumed value in the column 1. So here determine f dash pi for each assumed value of pi dash d as column 2. So this is the column 2. So once I know the f dash pi factor of safety, tan pi dash by tan pi dash d. Now in step 4, for each assumed value of pi dash d and beta, determine m, that is m1, m2. Okay, determine m from figure 15.23. So this figure. Okay. So I have assumed some value of the pi dash here, and I know the value of the beta here. So assumed pi dash d value, draw vertical line, so and intersect this line the corresponding to the beta value. Say for example, I have assumed beta pi dash of 15 and beta of say 60, beta of 60. So this is a line of intersection. From there you draw one horizontal line onto the ordinate. So this will give you your stability number. So this a value of the m. So once I know the m, then I know the relationship between m and c dash by gamma h critical. So just remember that gamma is known, h critical is known. So I can able to determine the c dash or c dash d. So let's see that. So from the each assumed value of pi dash d and beta, determine M using the chart that I shown. Then once M is known, so determine the developed cohesion for each value of the M which has been picked up from the figure 15.23. So the relationship is C dash, it's not a C dash, C dash original value. This is also mobilized cohesion, that is called as a C dash D1. So which is equals to M1 into gamma H. M1 into gamma H. So this is corresponding to initial assumed value. Now once I know the C dash D, which has been calculated based on the picked up value of the stability number, now I can recalculate the factor of safety as a function of the cohesion, which is defined as C dash divided by C dash D. Now C dash is a fixed value. This will not change. But C dash D1, C dash D2, this value will change depending upon the assumed value of the pi dash D. That means if you assume one value, you are going to get 1 FC dash 1, second FC dash 2, third FC dash 3, so on and so forth. But overall, if you look at the step number 1 to step number 6, actually we have calculated two factor of safety values. The first factor of safety value as a function of the angle of internal friction. The second factor of safety value as a function of the cohesion. Now I can develop a relationship between the FC dash versus F pi dash. The factor of safety as a function of the cohesion on the x-axis to the factor of safety as a function of the internal friction on the y-axis. So if you assume different values of the F pi dash and try to back calculate the FC dash value, and if you put everything in the graphical form, this is how it looks like. Now how to pick up or determine the exact value of the factor of safety as a function of the strength? For that purpose, from the horizon you need to draw an inclined line with inclination of 45 degree. So wherever this inclined line touches or intersects the graph, that would give you the factor of safety value. Now one condition is that when you try to develop the relationship between F pi and FC, both the axis values should be remain same. You cannot take non-uniform values, different values on the x-axis and different values on the y-axis. That is not possible. Okay, so both scales should be remain same. Then only so you can able to exactly identify the factor of safety, that is Fs, as a function of the strength. So here it is shown a small demonstration. So here given beta, gamma, C dash and pi dash. So required is H critical. So when I say H critical, so this is inherently makes an assumption that so the factor of safety with respect to cohesion, with respect to angle of internal friction, and with respect to strength are unity. So for a given beta and pi dash, so use the chart. So here beta angle of internal friction is 10. So corresponding to 10 and beta of approximately 45. Yeah. So draw one vertical line, and from there you draw another horizontal line. That would give you the stability number. So once I know the stability number, so which is nothing but M is equals to C by gamma H. But here H is H critical. So that is to be determined. So if you rearrange the equation, H critical is nothing but C dash by gamma into M. So where M is determined from this chart and C dash is already given and gamma is already given. So simply calculate the critical height. Okay. So this is that is how the friction circle method is used to determine the factor of safety. So alternatively, the Singh 1970, so he has given some kind of the predefined correlations, a bunch of predefined correlations, as we can see in this slide. So what he has done is he tried to develop the predefined curves between stability number, that is C dash by gamma h, versus the angle of internal friction pi dash versus the factor of safety. So earlier it was a different. Earlier stability number versus the internal friction versus slope angle. Slope angle. But instead of the slope angle, so he has replaced the slope angle with the factor of safety value. So the Fs is 2.5, Fs is 3, Fs is 3 are sorry, different values. So 2, 2.51 up to 1, so on and so forth. Okay, so either you can use these graphs or the original graphs. Both are welcome. Both should give you the same value. So this is the further contribution by Singh. It is in fact simplification of the Taylor's chart. There is nothing else. So same thing. Yeah. So there is another person. So right now we were discussing about only the rotational failure and assuming that the failure plane is circular. But apart from the circular, the people have also assumed some other forms. For example, Mikulovsky in 2002, what he has done is instead of assuming the failure surface as a circular, he assumed the failure surface as a log spiral, as you can see here. This is a log spiral. So when you say log spiral, the angle will keep on changes. So all along the failure surface, the angle keep on changes as well as the radius also not remains same. The radius also varies. As you can see, R0, R1, R2, R3, so on and so forth. So usually log spiral, actually this is the actual failure plane if you look at any book. So most of the failures happen in the form of a log spiral. But solving the equation by taking into account of the log spiral is very complicated one. That's why it is further simplified and assumed the failure surface as a circular. So this is further contribution by the Mikulovsky. So he has given the predefined charts for determining the factor of safety in homogeneous C5 soils. So he also gave some predefined chart, Fs by tan pi dash on the y-axis versus C dash by gamma h into tan pi dash on the x-axis for different slope angles ranging from 15, 30, 45, 60, 75, 90, as you can see from these graphs. Okay, so this is further. This is the contribution by the Mikulovsky. But these are the simplifications only. Either you talk about the Singh method or Mikulovsky's method. They are the simplifications of already developed methodologies. There is no new contribution in their methodologies. Here, this we will discuss in the later. Yeah. So that is one thing. Next, let us come to the method of slices. Yeah. Either ordinary method of the slices or Bishop's method. Okay. Let us come to the method of the slices. So as I told, in case of the method of the slices, so either the failure plane again same. It could be a slope failure or the toe failure or the base failure. And whatever the slip circle that you assume may not be a critical slip circle, which corresponding to the least factor of safety value. So it is a slip circle, but it will give you some factor of safety value, which might not be the least factor of safety value. That is possible. So therefore, numerous trials must be made in order to determine the least possible factor of safety value. It is an iterative procedure. It is not a single go, where in a single run we have done one circle and find it out that yes, this is the minimum possible factor of safety value. No. So which never ever possible in case of the slope stability analysis. Now here also, one of the important aspect is how shall I identify my center of the circle. So whatever the method you talk about in the slope stability analysis, it is utmost important to identify the center of the slip circle. It has very good implications in the real life situations. Because if I know at least the center of the slip circle, I can able to draw the possible failure mode. So here some procedure has been given by the different people. This kind of the procedure you may find only in few books. Actually, this is the information I try to compile from different people's presentations and from different books. Okay, so here let us try to understand. In the ordinary method of the slices, how to identify the center of the slip circle considering the toe failure. Considering the toe failure. So steps has been given. First, plot the configuration according to scale, that is embankment configuration as per the scale. Next, draw two lines from point A and point B at angles as has been shown in the figure. So at A, the angle theta 2, which is the acute angle between the line connecting the center to the toe and the slope, face of the slope. And theta 1, as you can see, so the line connecting center to the top of the embankment with respect to the horizontal. So if theta 1 and theta 2, so you can make any number of trials like this. Okay, you can assume any value of the theta 1 or any value of the theta 2 and try to draw the lines, and these two lines wherever they are meeting, so that would give you the center of the circle. So once center of the circle is known, by taking O and A as the radius of the circle, I can draw the possible slip circle. The possible slip circle. If this is the center of the circle, so if C and the O and A are the radius of the slip circle, so C as a O as a center, O as a center, OA as a radius, OA as a radius, I can draw the from the two a possible slip circle. Possible slip circle. Okay, so this is suppose if this is the least factor of safety, that is fine. It may not be asked. It may not be asked. So some values has been given for different slopes. For example, if the face slope is 1 vertical to half horizontal, or 1 vertical to 1 horizontal, 1 vertical to 1.5 horizontal, or 1:2, or 1 is, you can follow any of these things. And that is the equivalent slope angle, that is beta, is 60, 45, 34, 27, 19 as shown here. Then corresponding to this one, the possible values of the theta 1 and theta 2 are given here. Are given here. So, but these are only tentative values. They exactly may happen or may not happen at that point. So now, so having seen how to identify the center of the circle in case of the toe circle, now let us consider the base circle. Let us consider the base circle. So this is the base failure model. Base failure model. So in this method, what we need to do is, first you have to draw a vertical line at the middle of the slope AB. At the middle of the slope AB. Suppose, as you can see here, from A to B, so from exactly at h by 2 and h by 2. H by 2 and h by 2. So draw one vertical line. So draw a vertical line at the midpoint of the slope AB. AB. So the center of the critical slip circle always lies on the vertical line passing through the midpoint of the slope. Once this is line, so it is assumed that the center of the circle is assumed to be always lying on this vertical line. On this vertical line. So determine the center by hit and trial method by comparing the FOS. So for example, if I take at this location, at this location, as you can see, I can able to draw one critical slip circle. One critical slip circle. That is in the blue line. So corresponding to which the factor of safety is 1.65. Now if I shift the position of the center of the slip circle, so I can draw another slip circle that is shown by the red line. That is shown by the red line. So corresponding to which the factor of safety is 1.1. The factor of safety is 1.1. Okay. So but here also the crux is that you need to exercise several trial and errors until you have find it out the least or the factor of safety of the least value. That means again this is also very cumbersome procedure, very laborious. You need to make lot and lot of trials to find it out the possible least FYS value. It is said that angle made by the critical circle at the center is about 133.5. So as per the Fellini, yes. So the least factor of safety may possible. So if the angle between the two radiuses is 133.5 degree, 133.5. So this is the observation of the Fellini. So next, location of the critical slip circle in C5 soil. In the previous case, it is cohesive soil. Cohesive soil, case 1, toe failure. Cohesive soil, case 2, base failure. Next is the C5 soil. So how do you determine the center of the slip circle in case of the C5 soil? So in this case, so first of all, you need to draw an inclined line, such that you identify a point which is at a depth of at a depth of h from the bottom, either from the ground surface or from point A. H from the, if h is the height of the embankment, identify another point which is at a depth of h from the bottom, or h from the toe of the embankment, toe of the surface. That is one thing. Next, from the toe, identify a length of 4.5 times of height. 4.5 times of height. Now, it is certain that this horizontal line and the horizontal line corresponding to 4.55 times of h and the vertical line equivalent to h will coincide at some point at C. And now C as a horizon, draw an inclined line such that it cuts the slope AB at the middle. It cuts the slope face AB at the middle. So now once this line is known, again by identifying point, I can draw n number of slip circles, as shown here by red lines, like O1, O2, O3, O4, etc. All these indicate the centers of the slip circles. So if I say 1, 2, 3, 4, I can able to draw 1, 2, 3, 4, 5, 6, so many numbers of the slip circles, but each circle corresponding to the its own factor of safety value. So corresponding to which slip circle the factor of safety value is the least, that is the critical slip circle. So this is how the location of the critical slip circle in C5 soil will be identified. So that's all about identification of the center of the slip circle in pi soil for toe failure, for base failure, and C5 soil for toe failure. So this also we have discussed yesterday, and so this is the final form of the equation. For Bishop's simplified method of the slices. So here he also has given one free defined chart. All the charts will be provided in the exam, so you don't need to remember. So here you can see the chart is between alpha n versus m alpha versus tan pi dash by f. So all terms are there in this final form of the equation. So alpha n that is angle made by the trial slip circle with respect to bottom of the slice. So this part we leave it. Yeah. So now though we could able to derive the equations for different methods, but in reality there are several softwares available to determine the least factor of safety value. So for example, you can use the GeoSlope, GEO5, SV slope, or there are many softwares. There are more than 2 dozen number of softwares available to determine the least possible factor of safety by analytical means. So these are some important points about the Bishop's simplified method. So Bishop's simplified method is probably the most widely method. In fact, if you recall our all previous discussions, so after ordinary method of the slices, the next proposed method is only the Bishop's method. So after Bishop, so people took lot amount of a time to develop the computer codes. So theoretical development was there. So Bishop in the year 1955 he proposed the modified, he revised the ordinary method of the slices. But till then the people keep on theoretically modifying the equations, incorporating the side forces of each slice. However, it was a little impossible to calculate the factor of safety based on the manual or by manual. Okay, so it was the sophistication of the computer programs which made the life easy to compute the factor of safety within fraction of the seconds by employing any the difficult equations, any difficult equations. So like for example Bishop's method, so it is one of the difficult equations. If you want to do manually, we can still able to do it, but it takes immense amount of a time, while the same thing can be done in less than in couple of seconds if you use the computer program. So it yields the satisfactory results in most cases, and the FS determined, the factor of safety determined by this method is an underestimate, but the error is unlikely to exceed 7%, and most cases it is less than 2%. This is the reason the Bishop's method is extensively used in all previous practical applications. So on the other hand, the ordinary method of the slices is presented in the chapter as a learning tool only. It is used rarely now because it is too conservative. So because it doesn't account for any side forces which is supposed to be taken, and that is the advantage of, that is the merit of merit over the mass procedures. Then the Bishop's simplified method yields factor of safety which are higher than those obtained with the ordinary method of the slices. So the two methods do not lead to the same critical circle. That is true because ordinary method is based on the moment equilibrium, while Bishop's method is based on the both moment as well as the force equilibrium. So analysis by more refined methods involving consideration of the forces acting on the sides of the slices, so that the simplified Bishop method yields answers for all factors of safety, so which are very close to the correct answers, very close to the correct answer. So that means the refinement has led to not much accuracy, although it is. Okay, so that's what some important notes about the Bishop method. And when it comes to the practical conditions, so Morgenstern, so in the year 1960, so along with the Bishop, try to address some other problems. So for example here, they try to develop the correlations or the equations for the slope subjected to sudden drawdown condition, as you can see here. See for example, this is the embankment, this is the embankment, and this is the reservoir. This is the reservoir, maybe canal. The initial condition is that the canal is flowing with the full or upstream up to the high flood level. High flood level. So this is the water pressure on the sloping face of the embankment. Sloping face of the embankment. Now just imagine that in very short period of time, the water level was decreased from initial height to delta H. Initial height to delta H. Okay. Now this is happened so suddenly, that time is so short period, it won't allow the dissipation of the pore water pressure, within the soil, So this soil mass is still subjected to huge amount of the pore water pressure. So as a result of no dissipation of the pore water pressure from this soil, and upon the decrease or upon reducing the level, there is sudden increase in the weight of the sloping face. That increase in weight lead to the collapse of the soil. So collapse of the soil. That's why the sudden drawdown condition is so dangerous. So on the other hand, what if my embankment is subjected to the flooding condition? So this is the flooding condition. So suppose if you look at this slope, so on one side there is a flooding for a short period of time. On one side there is a flooding condition. But because of the flooding condition, the slope fails on the downstream side. On the downstream side. So it rarely fails on the upstream side. While if you look at the drawdown condition along with the flooding condition, in the case of the drawdown condition, in the case of the drawdown condition, the failure occurred on the upstream side. Okay, while in the case of the embankment subject to the flooding condition, the failure occurred on the opposite side. On the opposite side. Okay, so try to understand the logic between these two cases, but such cases were addressed by Bishop and Morgenstern. So these are the equations, steady state seepage. So this part also we have discussed yesterday. If you put the manometer at any depth, the rise of water level in this manometer is equivalent to up to the phreatic surface. So if you take the average pore water pressure, that is U is equals to gamma W into H or Hn, gamma W into H. And if you want the total force, multiply this with the width of the element, that is delta N. And these are the equations to determine the factor of safety for ordinary method of the slices. This is the equation. And if you want to inbuilt the term, the pore water pressure, so into this equation, so here you can see only small modification is required. In the earlier method, so where no pore water pressure was considered, only the normal force, that is W cos alpha n is straight away taken. W cos alpha n, that is normal force, straight away is taken. While if you account for the pore water pressure, so then you know the sigma dash is equals to so sigma minus u. So where sigma is the Wn cos alpha n and u is u into b, the original width of the slice. So this is how we can able to account for the effect of the pore pressure on the calculation of the factor of safety by ordinary method of the slices. So this part also we have discussed. Now when you consider any embankment, the embankment is the compacted one. The embankment is compacted. Therefore, the pore water pressure that develops should be a function of the normal stress also. The normal stress which is acting. So therefore, they try to define another parameter, that is Ru, is a non-dimensional quantity. This is pore pressure coefficient. So this is defined as Ru, a ratio of the average pore water pressure to overburden ratio. Ru, which is defined as the ratio of average pore water pressure divided by overburden pressure. So Ru is equals to Un by Wn. So this is the equation. See, for example, this is what we have discussed yesterday. Now I know the Ru is equals to Un by Wn. So Un is nothing but gamma W into H. That is the level of water rise. And sigma is equal to gamma into Z. And if you take the ordinary method of the slices, this is the equation. So here C dash is known, WLN, that is length of the slice, and Wn, that is the weight of the soil mass. So we also did discuss that your gamma is nothing but W, the total weight of the nth slice, which can be made equivalent to gamma into area. So area is Bn into Zn. Where Zn is nothing but average height of the nth slice. Nth slice. Now if you substitute the value of u in terms of the Ru and the value of W into the ordinary method of the equation, and if you simplify, so this is the bigger form that you obtain it. So this equation can be rewritten as in the form of Fs is equals to m dash minus n dash into ru, m dash minus n dash into ru, where m dash is nothing but maybe 1 by summation of b by h into z by h into sin alpha n. Alpha, no, yeah, sorry, it is the whole term, this entire term. You need to multiply, this one. Then here plus is there, so you can see the left side of plus is the c term, the right side is, this is anyhow 1 minus ru, 1 minus ru. So this can be written as 1, m dash minus n into ru. So the 1 multiplied with the 1 and another term multiplied with the ru. So that means if you compare this equation with this equation, it is obvious that the m dash is simplification of some terminology, n dash is simplification of the other terminology. Now that thing is a little advantageous, because if I know everything in terms of m dash and n dash, so I can propose some kind of the predefined curves. That's what exactly has been done. Here you can see they made the life so quite easy. In order to determine the factor of safety, so they converted everything into m dash and n dash and assume some value of the ru. So for stability coefficients m dash and n dash, for c dash by gamma h is equals to 0. C dash by gamma h is equals to 0, and stability coefficient for earth slopes. So 2:1, 3:1, 4:1, and 5:1. You take any slope angle, and if I know because once I know the 2:1 means I know the beta value, and I know the c dash by gamma h is 0. C dash by gamma h is 0. So I can able to calculate what is the value of the m, what is the value of the n dash. So for different values of the pi dash internal friction, and for the known value of the m dash and n dash, and for the known value of the slope angle, I can directly pick it up m dash and n dash value, m dash and n dash. Or otherwise, suppose if the slope angle is 2:1 and the internal friction angle of your soil is 20 degree, so you can pick up m dash value as 0.728 and n dash value as 0.91. So I know m dash, I know n dash. Straight away put these two terms in this equation. Fs is equal to m dash minus n dash into ru. Either you can assume some value, or alternatively you can directly calculate the value. Anything is okay. Okay. So these charts you can see m dash and n dash for c dash by gamma h is 0, c dash by gamma h is equal to 0.025, and depth is 1 meter. And c dash by gamma h is 0.025, depth is 1.25. C dash by gamma h is 0.05 and depth is 1. So c dash by gamma h is 0.05 and depth is 1.25. C dash by gamma h is 0.05 and d is 1.5. So you can use any of the chart depending upon your requirement. So continuation of the same. So G, H, all these tables, I, J, so many tables are there. So all these tables, the relevant or the suitable table will be provided in the exam. So you don't need to carry, or you don't need to remember all these tabulated values. MN, so that's it. So that's how the effect of the steady state CPS will be taken into account to determine the least possible factor of safety values. So this is the procedure. And there is another method, so that is by the Spencer solution, method of slices for steady state with the Spencer solution. The Spencer also gave the same procedure almost. So Spencer has provided solution to determine the Fs by taking into account the interslice forces, so which does satisfies equilibrium with respect to moment and force. So this is another contribution by the Spencer. So these are the charts proposed by Spencer. So C dash by Fs into gamma h for slope angle and for different Ru. Ru is equals to 0, Ru is equal to 0.25, Ru is equals to 0.5. And for different friction angles, So same further Michelovsky. So he also proposed another charts for computing the factor of safety when the slope is subjected to steady state CPS condition. Is Michelor viscous charts. So this will be it. Before that, let me show one of the important thing. So before, yeah, this also leave it. Leave it.
Sir, what is rhetoric surface?
What is
Sir, phreatic surface.
phreatic surface?
Yes, sir.
Phreatic surface. You don't know what is phreatic surface? You have seen your undergraduation program, na? Suppose say when there is a reservoir. So when you store the water for the first time, okay, the water starts seeping into the embankment. But when it is seeping, so it won't seep through the entire area of the embankment. Rather, it makes a particular line. So it is a line where the above is atmospheric condition and below is some pressure, seepage pressure. It exists. It is the interface between the atmospheric condition and the seepage pressure. Or there are some standard definitions also in several books. You can look into it.
Okay, sir.
Okay, so that is very fundamental. So, okay. Now, another important aspect that I would like to show to you is uh, there are several methods like Swedish method, that is Fellini's method, Bishop method, and refined Bishop method, Morgenstern and Price method, Spencer method, Bell's method, Ambo method, Sharma method. So how these each and every method is differentiated each other. So that differentiation you can able to understand from this simple assumption and the kind of the failure surface that they have considered and equilibrium equations that they have considered. Like for example, if you take the Swedish method, the resultant of the interslice forces is 0. Okay, then assumed failure surface is circular. It is only the moment method. On the other hand, if you take the Morgenstern and Price, the relationship between E and X, these are interslice forces, E and X, of the form, he has developed one relationship between, or he has given one mathematical function between the interslice forces, vertical and horizontal. Vertical and horizontal. And he also assumed any shape of the failure surface. Morgenstern and Price, any shape means circular, non-circular, planar, non-planar, it could be anything, doesn't matter. And equilibrium equations, it considers moment equilibrium, force equilibrium and everything. However, it requires a computer. You cannot able to simply solve by the manual. Okay, so other methods also, you can see the major distinction. So this is how different methods have evolved over a period of time. And this is the fundamental assumption and different method compilation of all the methods. Okay, so anyhow, it is recorded. So whenever you get a time, just go through how these equations are different. So then this is another summary about what kind of the force equilibrium equations that they have considered. For example, ordinary method of the slices, vertical force balance, yes, but horizontal force balance, no. Moment balance, yes. Bishop's method, vertical balance, yes. Horizontal balance, no. Moment balance, yes. Ambo's method, he has considered only vertical and horizontal forces, but no moment. Okay, so here we can see the complete summary about different equilibrium equations considered, different failure surfaces considered by the different people. And these are the different conditions under which a slope can fail. For example, a slope can fail under rapid drawdown condition or heavy rainfall over a short period of time, stage loading, or seepage analysis, steady state seepage, or transient seepage, or variable phreatic surface, or liquefaction, or flooding condition, or water table coinciding with the ground surface, or the material properties, either strain hardening or the strain softening. So we do not know which one is the actual cause for the failure of the slope. So any one factor or even multiple factors could contribute for the failure of the slope. Okay, so I will stop it here only. So this completes the theory part about the stability analysis. Maybe next class onward, we will try to solve, or I will try to take the tutorial. Okay. So if you have
So,
any quick, if you have
so
any quick question,
will we have any offline classes in the near future?
yeah, you received an email, na? You've seen.
Yes, sir.
There is one office order. You have to reach the campus on October 21st or something, they told.
So after that, will we have any offline classes, or it will
No,
continue?
no, no, no. In this semester, it is not possible to have an offline class.
Okay, sir. Thank you.